Okay, today we are going to continue on step 2, which is basically the trip distribution. So, what is trip distribution? Trip distribution basically that's the second step in the transportation four-step planning process. It comes right after the trip generation. Okay, so from the trip generation, we were able to produce trips or calculate the the productions and the attractions for each transportation analysis zone. So these are basically the inputs to the trip distribution. So what is the purpose of the trip distribution? The outcome from the trip distribution will be the number of trips going from one zone to another zone. So it's basically the trips between zone I to zone J. This is, we call it origin destination matrix. Okay, so this is what we need to calculate in this. So how what is the mathematical model governing this? Basically, we shall use the gravity model. What is the gravity model? The gravity model based on masses. So if you have two masses of production and attraction, okay, the closer the masses to each other, okay, and the larger the masses, the more attraction you have. The lower the okay. So here the productions, okay, this production or this production here is going to be distributed among different destinations. Okay, so each destination will have a pulling force, and it's going to be weighted distributed according to a weighted sum, like this. In other words, this is the gravity model, and this is the production, this is the attraction of destination J, and Fij, that's the friction between I and J, okay, and Kij, that's the socioeconomic factor between I and J, and here that's the summation of all pulls or all pulling forces from all destinations. So let's see what is friction, Fij. Fij is basically it's a function of resistance between the two masses. And in our case, for example, we take it the inverse of 1 over travel time squared between I and J. That means if we have two origin, two pairs far from each other, so that means the T travel time between I and J is very high. The F, the friction or the pulling force will be low. So it's, the friction is inversely proportional to the travel time. Any questions so far? Okay. Here we have a simplified version, okay, where basically we ignore the socioeconomic factor and we focus on the amount of attraction and the friction. And the friction function, as I mentioned, can be in this form or negative exponent form like this one, okay? So here we have an example that we started on last lecture, but we are gonna reiterate it or solve it again today. Here we have one zone, okay, zone 1, and that's the production from zone 1. The attraction is 0, okay. Here there's zone 2, zone 3, zone 4, and these are the travel times between the zones. So let's calculate the attraction, okay, or AI, AJ, I'm sorry, AJ multiply FIJ. So basically for zone, and here that's zone. So for zone 2, I'm sorry. Zone 2, it will be the attraction is 1000 multiply Fij is 1 over travel time square. So what's the travel time? 5. It's multiply 1 over 5 square. That means A2F12 equal, this is 25, so 1000 over 25, how much?
42.
40. A3F13 equal. So we have 2000 attraction divided by 100 equal 20. A4F14 equals 4000 divided by 20 square. So that means 400. So this will be 10. As we can see, zone 4 got the lowest pulling force. Zone 2 got the highest. Why? Because zone 2 is close to zone 1, much close to zone 1 than zone 4, for example. However, the attraction for zone 1, for zone 4, is 4 times the attraction at zone 2. So the trips from 1 to 2 equals, okay, before we go through this, let me just make the summation for J F I J, and J equals 2 to 4. So basically, what's the summation of all of these? This will be 70. So let's do the trip distribution, and let's calculate the trip, make the trip distribution here. So the trips from 1 to 2 equals, the numerator will be 40 divided by 70 multiply the total production, which is 200. What we are doing, basically, we are doing this. Trip I to J equal production of I multiply attraction of J multiply Fij divided by summation of AJ Fij. So that's the 70. This part, and this 200 is this part. Clear for everybody? So
Yes.
yes. So we have 40 divided by 70 multiplied to 100. This is going to be 114, sorry. 114.3. We're going to just leave it because this is trips. So trips usually are integer numbers. There is no half trip. And trip from 1 to 3 equals 20 divided by 70 multiplied to 100. This would equal to 57. Okay, trips from 1 to 4 equal 20 28 equal 10 divided by 70 multiplied to 100 equal 28. Actually equal 29 if we round the numbers. Okay, so let's add all these strips together. We will have 114 plus 57 plus 29. This would be 200. And these are trips. These are trips. Okay, so here the proposed project, there's a proposed project to build an expressway between zone 1 and zone 4. So the travel time will be reduced from 20 to 10. So let's see after this modification how things will be. And in order to do that, let's just reiterate on the problem again and just solve it again. Okay, so here let me just erase some of these. Okay, I'm sorry. Okay, so what's going to be changing here? The change we will have, basically, it will be in this component. The other two will remain the same. So this one, A4 F14 dash, will equal to 4,000 divided by the new friction, which is 10 square. Okay, so here the friction will be 40. So that means this will no longer be correct. It's going to change. So if we add 40, okay, plus 20 plus 40 is going to be 100. So this summation will be 100. Okay, so let's do the new distribution after. Okay, the new distribution, we will have T12 dash equal 40 divided by 100 multiplied to 100. So this will be 80. T13 equal 20 by 100 multiplied to 100. This will be 40. And T14 equal 40. That's the new trips between these origin and destinations. Over 100 multiplied to 100 equal 80. And these are trips. As you can see, there is a dramatic change. There is a drop in other destinations, and there is an increase in trips to this destination after just modifying the travel time from 20 to 10. Any questions so far? Okay, so here that's the example solved in a neat way. Okay, and here this is after building or after the modification of the building the expressway. Here we are going to have another example, and this example I'm going to solve it to you on Excel, because I'm going to show you few differences here. Hold on with me, please. So here is the problem that we have. we have three zones, and we have trip productions from each zone and trip attractions from each zone also. Let me just minimize this. That's the first table. The second table, we have the travel time between zones. So that's zone 1 to zone 1, that's 5, zone 1 to zone 2, and so on. So let's build here this array. First of all, that's origins. Origins. And here is going to be the destinations. Okay, so we have here zone 1, zone 2, zone 3, and we have here also zone 1. Let's just put it, okay, zone 2, zone 3. And here we have, for these origins, this is the production. So for zone 1, we have 140 production. Zone 2, we have 330 production. And zone 3, we have 280 production. For the attraction, we have attraction at zone 1, 300, and 270, and 180. Let's just make a check on the summation. So the summation here is basically set to 750 for both. Okay, so let's now calculate. I'm going to just put here let me just put these zones here. And this just origin slash okay. So let's put here, or let's just copy this one here. Here, let's put the friction or the travel time. The travel time here is 5, 2, 3, 2, 6, 6, 5. I'm sorry. 3, 3. Okay. 3, 6, 5. So that's the travel time. Based on this, we can calculate here the friction. So we're going to take the friction as 1 over T travel time square. So here, F equals 1 over TT square. So that means here will be, and let's multiply it, okay, the pulling force. The pulling force, this will equal to A J multiply F IJ. So here will be, what is the attraction at zone Z, so that's the attraction, okay, multiply 1 over the travel time square, okay, and actually this is going to be fixed in terms of rows. So this is going to be the pulling force. Okay, let me just check to make sure that we are, yes, that's correct. That's correct. Okay, as we can see that zone 2 so these are the destination, that's the origin. So between zone 2 and zone 1 there is a strong, you know, pulling force. Okay, between zone 3 and zone 1 there is a strong pulling force. Okay, between zone 1 and zone 2 there is a strong pulling force. Okay, okay, let's now do the second step, which is basically T trips I J, which equals to the production of I multiplied by A J multiplied by F I J divided by the sum of A J multiplied by F I J, which is basically this form, this equation. Basically, that's the trips. Okay, that's, we are, you know, calculating this form, this formula. Okay, so let me just copy and let's go to. So basically, this is this. But here we calculated the top part, the F. Okay, we need to calculate, you know, calculate the summation. So that's the sum of AJ multiply with the friction IJ. So this will be sum of these values. Okay, let me just arrange this in a better way that nobody will be confused. So the trips now between that's the production and that's the sum here. Okay, let's just copy it as a value. Paste options, values. Okay, so here the trips will be, these are the productions multiplied by the pulling force, which is 12, divided by the sum, which is here or here. Let's take this value. Okay, and this is going to be rounded with 0 digits. So this is going to be 17 trips. And the same applies to the rest, but we have to freeze some of the Okay, so here the production is one. The production is not going to change in columns. Okay. Uh, the same also here for the pulling force, the 12, it's going to be frozen on the row. No, it's not going to be frozen on the row, just moving. But the sum of AJ will be frozen in column. Okay, so now let's check on the sum of these trips. Check sum of trips here equal summation. Yani we are supposed to get basically the same production. Okay, perfect. We are getting the same production. It's perfect. Okay, now let's check on the attraction. Are we getting the same attraction or more? Equal sum. Oops, now it's higher. Okay, so here, that's the observation I was talking about last class, that there is going to be deviation between those and those values. So that was our first iteration. We need to make another iteration, until after distribution, we will end up with the same attraction values. ماشي يا شباب؟ هنا بوضح لكم مشكلة في الجرافيتي موديل. الجرافيتي موديل with after the first iteration بيحصل فرق ما بين التجميع، يعني لما بنجمع البرودكشن بيطلع واحد، لكن when we sum the attractions بيطلع فيه تباين. تمام؟ فبنحل ده ازاي؟ بنعمل تعديل في الاتراكشنز. اوكي؟ يعني هنا احنا كنا ده محسوب على اساس ايه؟ محسوب على اساس 300 وترافل تايم. لا، هنا هنضطر ان احنا هنعدل القيمه دي. تمام؟ و نشوف القيمه الجديده تبقى شكلها ايه، لغايه ما هنوصل في الاخر ان القيمه اللي بتطلع هنا هي الاوريجينال اتراكشن. تمام؟ ويبقى في حاله بالانس. واضح؟ اوكي، let's go back to the slides, and here let's see how we shall do this. So here that's an example, but here we were using a negative exponent, and after the total attraction here again in this case was different than the original attraction. Okay, and here we had to recalculate the whole thing again. Okay, in order to do this, we are gonna adjust the attraction based on the following relationship, which is basically the attraction for iteration k. That's the calculated attraction at zone j. So the attraction at the iteration k will be estimated attraction at j for iteration k, and this is the input attraction at j in iteration k minus 1. The resulted attraction at j in iteration k minus 1. So let's take this formula and see how can we benefit from it here. So we need to calculate a new attraction. So what is the new attraction? In our case, AJ, that's the original, 300. Okay, and let's just basically copy this over here. And here we're going to call it iteration to here iteration 1. So for the second iteration, we're going to calculate A, okay, here A, J, K equals the original attraction, which is basically the 300, correct? Divided by the calculated attraction, that's the resulted attraction, multiplied by the attraction in K minus 1, which is the same like here. So that means we are going to reduce the attraction. We're going to do the same for the rest. So here we are modifying the new attractions according to this equation. So the pulling force will be, instead of working with 300, no, here we are going to be working with 21 with the new calculated. So this is going to be like this, and this is going to be the sum. Okay, let me just check something. Okay, let's do the trip distribution again in the second iteration. So here it's rounded this value. Okay, good. And as you can see now, it's 350. And here is 228. And here 172. That's the original. These are the original. These are the original attraction. Now we are getting close. Let's do a third iteration, a second iteration again. Third iteration, we're gonna take all of this. Okay, so this is gonna be iteration 3, but I still have to modify some of the functions. So here we have basically this one is supposed to be the 300, the original 300 over there. Okay. Okay, that's the attraction. So this attraction, according to this formula, will be as following. It will be the original AJ, which is basically the 300, okay, divided by the AJ minus K, the one that we calculated here, okay. No, actually, the one that resulted here, okay, multiply with the input that we had in the previous one. So here it becomes this way. Okay. So now let's check on this. Okay, so this is the production. There is something wrong here. So this one is 150. Hold a second, let me just review this. So that's AJ. Okay, this is AJ, that's the 300, multiplied with AJK, okay, divided by 350. Okay, okay, here's the issue. This should be basically the new attraction, and the new attraction should be C 36. So this should be this attraction divided by, so that's a new pulling force. And let's just copy it here. Okay. Now you see that we are starting to get close to the original values, which are here. We keep doing this until we reach a point that there is almost no change between the calculated attraction and the actual attraction. So these are one of the disadvantages of the gravity model, that you need to do some iterative work until you get to that point. Clear يا شباب? Okay. So that was the gravity model, and how we are, we conduct this task. And as I mentioned, you keep iterating until you reach to a convergence. So this is after few iterations, we get to 301 and 270 and 180. Okay. Then we move now to the step after that, which is basically the mode choice. What do we mean with the mode choice? While transport, in traveling from an origin to a destination, there are different modes of transportation that we can use. We can go by car, we can go by bus, okay, or we can use subway. It depends on the available modes of transportation. So, on what basis travelers select their mode? Okay, it depends on several factors. Some of the factors that make drivers take the decision or affect their decision is basically the travel time of the mode. Okay, for example, if you want to go downtown in New York, for example, okay, you won't be inclined to drive your own car. You will drive. You would like to. You would prefer to take the subway. Okay, for many reasons. First of all, congestion and travel time. Okay, and also for parking cost. If you park your car in Manhattan, for example, it will cost you a fortune. Okay, and also crossing the bridges or the tunnels. Okay, that's you are paying tolls on each of these. So that's another, and for convenience and for safety. So these are all factors that plays a role in drivers' decisions or traveler decisions in which mode to use. So people's working in the psychology area and human behavior were able to come up with a logit model. Okay, logit model, this is a negative exponent model that basically determines the selection, pattern for users for certain choices or decisions. And they define that the logit model uses a relative utility, which is utility function, UX, which is basically a sum. It's a weighted sum for all of these factors. So UX, that's a utility function, and it's summation of AI multiply XI, where N, these are the number of attributes that you have for the modes, and XI, that's the attribute value, whether time, cost, safety, whatever. AI, the coefficient of the attribute. The coefficient represents basically how important this attribute to the users, and how, the weight of, it affects their decisions. So then if we have, for example, two modes of transportation that we need to determine the probability of selecting either mode A or mode B. So for selecting mode A, it will going to be the probability of selecting mode A equal e to the power utility of A divided by the sum of e to the power utility of A plus the utility of B. To better understand the mode choice, let's have an example. Okay, so we have now three modes of transportation: car, bus, and subway. Okay, and we have four attributes: travel time, walking time, and cost, out of pocket costs in cents, and CV, that's a convenience factor, and it's from 1 to 10. So the car is 3, the bus is 4, the subway is 5, the cost, okay, for the car is 450, for the bus is 120, and so on. And this is the utility function that is governing, okay, these modes of transportation. So let's calculate the utility function for each mode. First, we need to calculate the U of each mode, or the utility for each mode. So let's calculate U. Okay, let me just modify something here. So let's move this up. So we have a space that we can work in. Let me just remove this. So now we want to calculate the utility for each of these modes. So U car equal minus 0.55 multiply 18 minus 0.45 multiply 10 minus 0.01 multiply 450 minus 0.20 multiply 3. U bus equals minus 0.55 multiply 25 minus 0.45 multiply 12. I would appreciate if someone do the calculations while I'm writing the equation. Minus 0.01 multiply 120 minus 0.2 multiply 4. And the utility for subway equal minus 0.55 multiply 24 minus 0.45 multiply 6 minus 0.01 multiply 200 minus 0.2 multiply 5. Okay, what are the results here?
The first one is minus 19.5.
Okay, could you just repeat that, please?
The first one is minus 19.5.
And the second?
The second one is minus 21.15.
And the third?
I'll calculate it now.
Okay, thank you. And what are the units, by the way? There is no units for utility functions. As you can see, it's a function that aggregate different values with different units in one formula. Okay,
The last one is minus 18.9.
18.9.
9.
So now let's calculate first of all the e to the power u car, e to the power u bus, e to the power u subway. This is going to be 3.398 multiply 10 to the power minus 9 this 21.15. This is going to be 6.53 10 to the power minus 10, and this will be 18.9 6.19 10 to the power minus 9. So let's calculate the probability of using cars equals. Let's see the sum of E utility I. What is the summation for all these functions? It's going to be 6.53 E minus 10 plus 3.398 E minus 9. So this is basically 1.024 multiply 10 to the power minus 8. So multiply 3.398 e to the power minus 9. So this will be 0.3317. Probability of using bus equals 6.19 okay, E minus 9. So this is 0.604. No, that's wrong. This is minus 10. Can someone please repeat this again with me or calculate with me? So the first one is correct. The second one That's 6.53 E minus 10 divided by 1.024 E minus 8. Okay, so this one is basically 0.0637, and B of subway equals 6.19 e to the power minus 9. So it's 0.6045. What does this mean? These values, what does it mean? It means that the probability of using a car is 33.17%. Probability of riding a bus will be 6.37%. Probability of using a subway will be 60.45%. That means if we have a production, we can distribute these, or if we have trips between origin I and destination J, and they have these modes of choice, then this is going to be the better. Not all trips will be going by car. Only 33% will use their cars, and 6% will use the bus, and 60% will go by subway. Clear?
Doctor,
Yes.
if we added the last three number, we will get 100%, right?
Yes.
We can check from this if our calculation is right.
Yes, we can have a check now. Let's just add the 60% 0.45 plus 6.37 plus 33.17.
It's equal 99.99.
99.99%. And this is due to rounding. As you can see that we are doing rounding all over the place here. So this difference is due to rounding. So this is almost 100%. We can live with that. Okay? Clear?
Clear, Doctor.
Okay. Let's move on to, that's the solution of the problem. And this is the probability of using cars and, different things. Any questions? Okay, we're going to take a short break and we'll be back after exactly 10 minutes from now. We're going to be back at 3:15. Okay, we are back. Now we are going to discuss the mode choice function, or the utility function, and how can we use it, okay, to change these probabilities. Okay, so here, for example, we have the subway. We have 60% of the travelers attracted to the subway. Maybe this is higher than the capacity, and maybe we want to reduce this value, for example. And the bus service, we have only 6% attracted, so we might need to increase it, and this one reduce it. How can we do that? The utility function, we use this utility function, okay, to modify this distribution. So in other words, we might, for example, for subway, okay, increase this cost. So this way, people will be less attracted to the subway. And we might, so this might go up and this might go down. However, the travel time, it's hard to change. For bus, we can, look for an HOV lane, high occupancy vehicle lane, okay, and see if it's gonna change. The walking time, that's the bus stop. The distance, the average walking time to the bus stop here is 12 minutes. This is difficult to change. So basically what we have to change, or the convenience we can change, also modify it. But the cost, that's usually the most handy option for us to change in order to change the distribution probabilities. Clear? So how can we, so this here, the probability, okay, of using alternative A dash, that's after change during to modifications, okay, will be the probability of A multiplied by delta UA over a probability of I multiplied this. You can use this form, or simply you can just go back and recalculate these values. Okay, so in our case, let's try modifying. Now we want to improve the utility of bus. This is our target. Let me just make a copy here of this. So this is our table, and this is our utility function. So now we are going to change. Let's try first of all to change instead of 200, we're going to have here, for example, make it 240. And the cost of using the bus, we are going to make it maybe 100 cents or 75 cents. So we are reducing the cost of using the bus, increasing the cost of using the subway. So based on this, the utility function for the car did not change, correct? Here, let me just have a look at this. So here, as you can see, the first line, there's no change. But here we are going to have to change this to be 75, and this one will be 240. So this is going to be reflected here in terms of utility function value. So this one will be minus 21.15 plus 45 multiplied 0.01. So this will be 20.7. And for the subway, this will be after modification is going to be minus 18.9 plus 40 multiplied 0.01. So this minus, this is going to be 19.3. Based on this, we can say that the E car equal how much is going to be the same, did not change, correct? But E bus and E subway these are going to change. So the e to the power minus 19.5 is going to be as it is, 3.398 multiplied 10 to the power minus 9, and the other one here is 20.7, so this one is 1.0235 multiplied 10 to the power minus 9. The third one is going to be 19.3, so here it's 4.15, 1 multiplied 10 to the power minus 9. The sum of all of these is going to be basically it's 4.151 plus 1.0235 plus 3.398 and all to the power 10. So here's going to be 8.57 sorry, to 5 multiplied 10 to the power minus 9. So now the new probabilities for cars, is it going to change or stay the same? What do you think?
I think it will change.
It will change. Definitely it will change. So this one is going to be 3.398 divided by 8.5725 multiplied 10 to the power minus 9 divided by 10 to the power minus 9. So actually the power goes this way together. So it's going to be directly multiplied 3.398. So this one now is 0.396, which is 39.6%. What was the previous value? It was 33. It was 33. Now it's 39, because when we increased the cost here, some of the travelers went here and some will go here, as you can see. So B dash for bus equal 1.0235 divided by 8.5725 equal
0.119.
0.119.
119.
So that means 11.9%. Okay, there is a change, but not that much. The probability for using the subway equals 4.151 divided by 8.5725 equals
0.484.
484. That means it's almost 48.4%. As we can see, there is a drop. It's expected that we'll have a drop in but the cars or the mode of the cars attracted significant portion, okay, of those that left the subway. So what's the solution? We can change this value. How can we change this value? You can change the parking fees, for example. Okay, that's one option. The second option also to decrease this value and increase the parking. Okay, so these are options available that we can use and tweak to change the pattern of or the distribution in the modes, as we can see in this example. Any questions so far? Actually, mode choice, usually several companies use it in transportations for different applications, you know, and for in different contexts, not just for transportation planning, even for airlines. Okay, especially if you have a connected flight and connection, you know, so if there's a connection between two links and the waiting time is long, okay, they try to reduce the cost in order to attract more travelers and so on. And we will elaborate on that in next week, inshallah, with different examples. Any questions so far? Okay, the next step that we will, you know, discuss next week is basically the trip assignment, which is basically how we assign those trips to the transportation network. And we will discuss that next week, inshallah. Okay, I will, you know, I will end it right here. And if you have any questions, you may ask your questions now.